distinguished speaker today, Professor Hiroshi KORI, who is waiting. And what he's going to speak on is parameter based on phase oscillators, phase oscillator modulations, and from oscillatory spike data. So he spoke for us in a meeting just 2 years ago. And, he was actually live, and it would have been nice if he could have come, but it's very kind of him to actually come. So I hope you can hear you, Hiroshi. Welcome.
Yeah, yes, I can hear you. Oh, can I start already? Yes, okay. So thank you very much for your kind invitation. I'm sorry that I could not come to India, but I hope you can enjoy my talk online. So my name is Hiroshi KORI from the University of Tokyo. And today I'm going to talk about parameter inference based on phase oscillator models from oscillatory or spike data. Okay, so I'm theoretical physicist working on synchronization, and at first I would like to show you a nice movie of synchronization. Here you can see 4 metronomes on a bridge, and you can see the interaction between metronomes. And now you can see two clusters, 2 small amplitude, 2 large amplitude, and this is a kind of quasi-steady state, but this is unstable, and eventually they find synchronous dynamics, and this is in-phase synchronization. Now you can see 4 oscillators are almost have the same phase and same amplitude, so close to complete synchronization. Okay, so this kind of synchronization dynamics occurs everywhere. For example, our circadian clock, it's about 24 hours rhythmicity of our body. Is also organized by synchronization. There is a tissues called SCN. It's inside the brain. It's a population of neurons, about a few thousand neurons, and there you can see also nice synchronization dynamics. Here, each individual cell has genetic oscillations of about 24 hours rhythm, and by neural network, so they communicate using certain neurotransmitters to communicate, and then eventually they synchronize. Okay, so the aim of this talk, this study, is network inference. So let us suppose that we may observe oscillatory signals xi of t from a network of noisy oscillators. For example, if we have 2 oscillators, we suppose that we can observe this kind of oscillatory data from individual oscillators, and want to infer coupling strengths, or in the case of population, coupling network of oscillators. So this is our aim. And there are many challenges in this type of problem. One challenge is inference for synchronized oscillators. Suppose that we have 2 oscillators and they are asynchronous. In that case, we have good information of the system because the trajectories can go a lot of places in the phase space, but in the case of synchrony, there is a certain manifold, and the dynamics is confined in the vicinity of a certain manifold, synchronization manifold. That's why we have only limited information, and in this case, certainly the inference becomes difficult. And to circumvent this problem, maybe we can give some strong perturbation to the system, and then we can have many trajectories in the phase space, and then we can obtain more information about the dynamics. But this kind of perturbation, we may face experimental or aesthetical problems in some cases. So we want to develop a non-invasive inference method. I mean, we do not give such strong perturbation to the system, just observing the system as is, and we want to achieve the inference. So that is our target. And for this aim, we use this method, so inference based on phase oscillator models. So suppose that we have oscillatory signal, and then we reconstruct phase somehow. So from oscillatory signal, for example, you can use Hilbert transform to reconstruct phases of each individual oscillators. And then we get the time series of phase. And this phase is fitted to a so-called phase oscillator model. For example, we may have this kind of simple coupled oscillator system, Kuramoto type phase oscillators, plus some noise. And by fitting this time series phi to this phase oscillator model, we can infer coupling strength or noise strength. So that is what we want to do. And we will show that this method, if we use this kind of so-called averaged phase model, I will explain in detail later. This method may cause a large error of order of coupling strength. And what we want to infer is of order k quantities, that is a coupling network. So actually this method doesn't work. And instead, we are going to propose a different method to overcome this problem. That is already reported in this archive paper. And after that, I will also propose another very different method that is already introduced in this paper. And I would like to emphasize that both methods work for synchronized oscillators, not only for asynchronous oscillators. No, sorry. The first method works for both asynchronous and synchronous oscillators, and the second method can work for synchronized oscillators. Okay. And before going to show our method, I would like to introduce the phase reduction theory, because our method is based on phase oscillator models, and the detail of phase reduction theory is needed to explain why this method doesn't work and why our proposed method will work. And the phase reduction theory is established in this book by Yoshiki Kuramoto in 1948. No, 84. Okay, suppose that we have a limit cycle, for example, metronome. And metronome is a good example of limit cycle oscillator. Anyway, starting from certain initial condition, this will converge to periodic orbit that is called limit cycle. So if we draw phase space, we have this kind of trajectory. So starting from certain initial conditions, this will anyway converge to one isolated periodic orbit. So we consider this type of oscillator, and this is phase oscillator. So suppose that a single oscillator, limit cycle oscillator, for example, it can be metronome or genetic oscillator, is perturbed weakly. Then we can expect that we can describe the dynamics by a single variable model, so-called phase oscillator model. And the equation looks like this. So phi is a phase of oscillator, and phi is defined in such a way that single oscillator case, the natural frequency becomes constant, not phi dependent. So this is just constant, plus the effect of perturbation. And P is a perturbation directly given to limit cycle oscillator. And in the phase equation, it's not, the P does not directly come to the equation, but it's a multiplication between this function Z and P. And this Z is called phase sensitivity function. So suppose that we have positive perturbation. In that case, sometimes the oscillator becomes speed up, and this information is expressed by the Z, that is the Z having positive value. So in this case, the phase, this oscillator becomes speed up. And if phase is in this region, then the positive pulse makes the oscillator become slower. So this is expressed by negative Z values. So we generally have this kind of phase sensitivity function if we transform the limit cycle oscillator to the phase oscillator model. And this is a way of derivation of phase oscillator model. Now we have limit cycle oscillator, and we define phase such a way that in a single oscillator phase space, the phase evolves with a constant frequency omega. And actually this phase is defined as a scalar field in this phase space. Okay, and by defining this phase, we can derive the phase equation in this way. So d phi dt is phi d phi dw, and dw dt, this is just the simple calculus, and then we get this type of equation. And here you can see we have the gradient of phi with respect to the state variable x. And this kappa p is a perturbation. And by neglecting higher order terms, we get this phase equation. Now this is closed in phase. So the phase derivative of phase is constant velocity omega plus this term. So this model is already shown in the previous slide. And this Z function is sometimes called infinitesimal phase response curve or phase sensitivity function. Okay. Now, this is the example. Suppose that we have two fireflies and communicating using the light pulse. So this is one firefly and this is the other firefly. And suppose that this firefly emits light as a function of phase in this way, periodically. And also we suppose that these fireflies having different natural frequency omega. Okay, in this case we can have this kind of phase oscillator model. So the oscillator 1 has natural frequency omega 1 plus this term is effect of perturbation coming from the second oscillator. Okay. All right. So by the way, this type of phase equation, the merit of using this type of phase equation is that we can directly quite often measure these quantities of interest. For example, omega can be directly measured by observing the single oscillator behavior, and Z can be measured experimentally using some techniques, and also P is, for example, in this case, light signal. So these quantities can be experimentally observable, and so we can construct phase oscillator model out of the experimentally measured quantities. Okay, and we can further simplify this kind of phase oscillator models, so-called to the averaged phase oscillator model. And the procedure is as follows. So we have this model, and let us assume that, oh, sorry, I forgot the important thing. So this derivation, I neglected all the kappa square term. So here I assume that the coupling or the perturbation is sufficiently weak. And the phase oscillator model is valid only when this kind of the perturbations are weak. For example, the coupling from other oscillators or the effect of noise are sufficiently weak, then the phase oscillator model provides a good approximation to the original model. So again, we assume this one. So the coupling strength is, in this case, much smaller than the natural frequencies omega-1 and omega-2. Then the phase difference between two oscillators does not significantly change within one cycle. And one cycle is defined by this capital T. Capital T is 2 pi over 1 omega-1. So this is natural frequency of oscillator 1. And so to understand this averaging approximation, we integrate this variable over one cycle. So let us see this value phi1 t plus capital T minus phi1 t. And this is a simply integral of this flow, this velocity over time t. So this is the integration, and now we do make some estimation. So the phi1t can be expressed in this way. Phi1s is phi1t plus omega-1s in a good approximation, because this kappa term is small. So in a good approximation, this can be replaced by this one. And the similar way, this term can be replaced by phi2t initial point plus omega-2s plus some error term. Okay. Now next, this omega-2 can be further approximated by omega-1 if the difference between omega-2 and omega-1 is sufficiently small. And the error terms is evaluated like this, delta omega. Delta omega is the frequency difference between omega-1 and omega-2. And these errors are actually multiplied by this coupling strength kappa. So these would be the higher order errors if we shift if we eliminate these terms from the integral. So you can see this is already higher terms, higher order errors compared to this coupling term. So we can, in a good approximation, neglect these terms. And we can perform this integral because this is a constant. This is a constant inside this integral, and this is just the integration over one cycle, and then we get this equation. Actually, I'm sorry that can you see this bar here? Probably yes. So maybe we should eliminate this one. One moment, how can I do this? Why is this here? Interesting, one moment. I don't know why this appears here. Interesting. What is happening? One moment. Display. Desktop. Okay, good. Now we have, can you see the screen? Yes, okay, good. All right. Okay, so we have this f, function f, and this is so-called phase coupling function. Now this is a function of phase difference and much easier to treat than this type of coupling function. Okay. Now, further simplification. So we originally have this type of equation, and we obtained this equations. Okay, and this can be regarded as a circle map. So the given phi1 value and phi2 value as a function at time t, then we will know the phase of time t plus capital T one cycle later. Okay, and by dividing both sides by capital T, then we get this equation. Now, we can consider this rough approximation by replacing this by the derivative of phi1, and by neglecting these higher order terms, we get this equation. And this is so-called average phase equation, and the Kuramoto model is certainly of this type. So in the case of Kuramoto model, this function f is sine function. But anyway, the important thing is that this is the function of phase difference. Now, question is that by comparing this type of equation, this equation, how good or bad is this approximation? And here, using a certain example, I will show how large is the error between these two equations. So suppose that this is the original model. In this case, just one oscillator and having this type of perturbations. And this is the average equation. If you simply do the averaging approximation, one can drop this term, because in this term there's no the offset. So the constant part is there, so we can just simply drop this term. And this is the numerical simulation of these two equations. And the blue one is the upper one, and the orange one is the bottom one. And here I'm plotting the phi t minus t as a function of time. And you can see there's a large difference between two trajectories. And now let us estimate this difference. Okay, so the averaging approximation is actually done through certain nonlinear transformation. So let us introduce about this nonlinear transformation. So suppose that we have this type of model. So S is any periodic function of phi, and the certain nonlinear transformation is called so-called near identity transformation. And by this transformation, we introduce a new variable phi, var phi, and which is given in this way. And this is called near identity transformation because phi and phi are almost the same, except for this small term of order kappa. And here, h function is chosen in this way. This is basically the integral of s phi, and with some manipulation here. And applying this transformation, we get this type of equation. So you can directly calculate the phi dot, then you will be convinced that you will get this equation. So this is actually the averaged equation, right? If we neglect over the kappa square term. So through this nonlinear transformation, we can understand that the averaging approximation is good approximation because the error is higher order than this perturbation term. So we can safely neglect this term if we consider small enough, sufficiently small kappa values. We can safely neglect this one. But we have to be careful that actually this phi and phi, bar phi, are not very similar because of this transformation. You can see the differences of order kappa. That's why we generally have this large deviation. So generally the average equation, the non-average equation and average equation having the distance of the same order as the perturbation term. But after one cycle, the deviation is small. This is higher order term and can be neglected if kappa is sufficiently small. Okay, so this is a brief summary of phase reduction theory. So if we have a real system, one can, for example, obtain this kind of detailed oscillator models, and out of this detailed oscillator model, we can derive this type of non-averaged phase oscillator model at first. And here the error is kappa square. And by this nonlinear transformation, we can further simplify this equation into the average phase oscillator model. And again, the error is of order kappa square, so one can safely neglect this. And then we can understand the phenomenon. And as I told you, actually the variable phi and bar phi are different. Then the difference is of order kappa. Now we can go to the, so I would like to go to the inference method. Maybe we can skip this one. Sorry, I forgot the time. Until what time can I talk? Sorry, I don't remember what time I started.
You have time till 10:10. You hear?
10:10. Okay.
10:10. And we started about 4 minutes late.
Okay. So I have 5 minutes
have
more.
Time till about 10:15. Okay. But please leave a few minutes for questions.
Yeah. Okay. So the method one. Okay. Method one is. So we would like to infer the phase offset. The network using from this oscillator signal, we reconstruct phase somehow and then fit this data to the phase model and infer network. But as I told you, if we use this method, so just simply fitting this phase to the phase oscillator model, we call it, this is naive method. Actually, the network inference doesn't work, as you can see. So this is true network. So the artificial data is made from coupled oscillators. And this is true network, but this is inferred network, so totally different. So one of the reasons is the reconstructed phase does not obey the average phase equation. So that is a problem. But if we use not the average phase equation, but this type of circle map, then actually the inference works. So this is the case of naive method, and this is our proposed method using this circle map. So we use inferred the reconstructed phase only every period, every t period, and then fit these phase data to this model. And then we can infer the coupling strength C and noise strength, in this case, sigma. And then the inference works. And then the reason why this is better than this type of phase model is, as I told you, this model may have a significant error because generally the phase variable does not obey this equation. But this equation is has the smaller errors, and then we can expect this method works, and it actually works. So this is method 1. And about this is about method 2. Not from oscillatory data, but we consider this type of spike data in this case. And this is a model to describe the spike statistics. We consider this type of non-average phase oscillator models, and the spikes are defined in this way, and we can define these variances of time needed for M spikes, and also variance of spikes between two spikes, the two oscillators. And then we obtain this formula out of these phase equations, and this is effective noise strength, and this is effective coupling strength, and these are function of this Vm and S. And so from experiments or from data, we can calculate this Vm and S, and then from that we can infer the coupling strength and noise strength. And actually this works also. For example, this is a case of diffusively coupled Fitch-Funag oscillators. We show that this works. Okay, so this is a summary. So we propose two methods for network inference based on phase reduction theory, and method 1 is use oscillatory data, and method 2 is use spike data, and both works. And I didn't really emphasize, but both these method works for synchronous oscillators. This is a very important thing. Okay, thank you very much.
So you did that very efficiently. So we have for 2 or 3 questions. KORI?
Can I ask? Can you hear me?
Yes, I can hear you.
Okay. So suppose you are given, I don't understand the details of the math here. So if you're given a recording from a network with spike data, I know there is some interacting network. It's made up of links which are inhibitory and excitatory in neural network terms. So if I have simply the spike data from the population, from a subset of the neurons, in that, you think you can infer the network using these methods?
Yeah, thank you very much for the question. So actually, I didn't explain carefully, but actually, this method 2 is formulated only for 2 oscillators. So we didn't consider a network of oscillators. So we have to extend this work to a case of networks. This is a future work.
Can I ask?
Yes.
Yeah. So since you're considering averaged circle map, is there any improvement on the weakness of perturbation that you consider to original Kuromoto model and this? Like all the phase model works for weak perturbation. Considering this additional averaging, is there any advantage that it will work for slightly stronger perturbation kind of a thing? Is there any quantitative advantage of that?
Yeah, the point is that if we use these average phase models, so a big problem is how to construct phase out of oscillatory data. So this is actually a difficult task. So for example, we can use Hilbert transform to reconstruct phase, but we don't know how good these phase obeys this kind of average phase model. So that was a problem. But in the case of circle map, we expect that we show that the error is small here. So the higher order error, only higher order error arises in this circle map. So that's why we use this circle map. And I hope, did I answer to your question? Can you repeat your question?
Okay, yeah, that kind of makes sense, like to some extent, yes. Thank you.
Yeah, thank you.
In fact, on this very slide that we are looking at, which is, see, it's the average phase which you're talking of, which maps to a circle map, or you can take the circle map and use the average phase, which is the, what exactly are you saying? The circle map.
Yeah, this map.
Yes, is directly from the original equation, right? Or
this equation.
Yes. So are you substituting the oscillators, the phases of the circle maps for the phases of the oscillators, or are you doing anything more?
Sorry, I couldn't hear well, so can you repeat?
Else, are you substituting the oscillators, the oscillators with the maps, and that's it? Or are you doing anything more?
Oh, I see. Yeah, I simply use this dynamical equation.
Yes.
Yeah, more precisely. Yeah, this dynamical equation.
Okay.
And fit phase data to this equation.
This equation.
Yes.
All right. So if there are any other questions? So Hiroshi, thank you so much.
Thank you very much.
You see if it's possible for you to do it or not. It is that we have a discussion session from 11:10 to 11:30 our time. Okay. So would you like to participate?
Yeah, actually, I have to
Have the time-
leave
you have
here
the time.
right now, so I'm very sorry about this. Can you hear me? Yeah.
You'll not be able to join. Oh, okay.
Yeah, sorry, I have to leave. Yeah, right now. I'm sorry about this.
Okay.
Okay, thank you very much.
Thank you so much.